So this last activity for today gives us a system of equations that does not have the same number of variables as it has equations. We've got 4 variables going on in here, but we only have 2 equations that bind them together. So if we're thinking geometrically about what each of these equations represents, these equations no longer describe lines anymore. What they describe are called hyperplanes. So each of these equations describes a 3-dimensional flat surface inside of 4-dimensional space. And so we're kind of taking 2 3-dimensional things and trying to intersect them together, which, as you might expect, is a lot more complicated than taking 2 lines, which are 1-dimensional things, and intersecting them together. In fact, the very idea of dimension is one that we have to, in linear algebra, put onto a firm foundation. It's part of what we do in that chapter on vector spaces. So right now I'm just using the term kind of loosely. But the idea is because we have 2 more variables than we have equations, probably our solution set is going to be pretty big, right? Even if I take 2 two-dimensional surfaces, 2 planes, and I intersect them together, I get a whole bunch of different points that lie along the intersection of 2 planes. Generally, in general position, they intersect in a line that we can describe using a similar strategy to this. So this activity tries to walk you through the process of describing this solution set. And the way that it does it is it takes 2 of these 4 variables, x2 and x4, and we don't yet know why those 2 are the ones that we're choosing, but we'll see that by the end of this chapter, and says, if I just rename those variables into meaningless parameters, if I just call one of them a and the other one of them b, the idea is this, that if I solve for the other variables, x1 and x3, that I will be able to solve for x1 and x3 in terms of a and b. And if I can do that, then what that means is I can describe all the points in this solution set through what I called earlier today in multivariable calculus a vector-valued function. Basically, a function that takes 2 parameters, a and b, as input, and as output it produces for me a vector in 4 dimensions, so this 4-component vector, and that those vectors are the solutions of this equation. And because there's infinitely many choices that you could make for the parameters a and b, that means there's infinitely many different points that can be produced as the solution of this system. So how you describe it is by identifying variables that you want to be the meaningless parameters a and b, and then solving for the other variables in terms of those meaningless parameters, and then just packaging those things up as a vector. And so ultimately what we end up doing to package this thing. So let me just put this observation in here before you get started on this work, because I think this is one of the points that ends up being the most confusing when we do this. So what we end up wanting to do is determine, so we end up wanting to describe a solution set. And my solution set is going to be a bunch of vectors, 4-dimensional, 4-component vectors, right? And so what we're doing when we try to describe such a thing is we just want to specify what are the values of each of the 4 components. And the first component is the component we would call x1. The second component is the one we would call x2. The third component we would call x3. And the fourth we would call x4. And so what we're really doing when we're trying to describe one of these solution sets is, once we decide that x2 can be described by some meaningless parameter a, and that x4 can be described by some meaningless parameter b, then we have to figure out what x3 can be described by and what x1 can be described by, and these are going to probably be expressions involving a and or b. And we would use the system to solve for what those expressions would be. So this is kind of what we're doing. So we pick 2 of my variables to be replaced by meaningless parameters, and then we solve for the other variables in terms of those meaningless parameters. And then we would use this set builder notation to say that the solution set is the set of all vectors that have that form, where a and b range over all possible choices of real numbers that we could pick for those parameters. We can expect this to be something we have to do anytime we have what's called an underdetermined system, where we have more unknowns than we have equations. So we don't have enough equations to bind us to a unique solution, right? So we can always expect to do this when we have a sort of a wide system that has, sort of more variables than it has equations. But that doesn't mean that it doesn't sometimes happen for square systems that have the same number of equations as variables, or for tall systems that have more equations than they have variables. It's always a possibility, but it's a guarantee anytime we have more variables than we have equations. And we'll understand why that is gradually over the course of the next few weeks.